So Matt and Libby and I are just going to give an overview of the science and what's known about the science of, thank you, of climate change and its impacts on New Zealand's marine environment. Right, so I'm just going to flick through. Okay, so this diagram up here is from a report that a few of it, or a whole lot of us actually have recently completed, trying to understand what kinds of changes we might expect around New Zealand in the ocean and the coast, and what's already changed so far. So there's a whole lot of stuff that won't be a surprise to you listed down the side there. I'm going to talk a little bit more in detail about those 5 things on the left just this morning. Okay. Sorry. So first of all, temperature. So we all hear a lot about warming. Sea surface temperatures around New Zealand have definitely warmed over the last 20 or so years, and that diagram there shows how they have changed and how that varies regionally. The actual increase over the last 20 years is quite small, but there are definite hotspots that you can see up there. So particularly around the northeastern New Zealand. There have also been heat waves, which have been in the news heaps. So we know about that. They affect the upper 20 to 40 metres of the water column. And in terms of what's projected to happen, by the end of the century, we expect that the oceans will be almost 3 degrees warmer. And most of the warming is going to be in the Tasman Sea and the subantarctic waters south of the Chatham Rise. So what might that actually do to our marine environments? Okay, sorry. We could anticipate that there'll be shifts in distributions of fish species, for example, changes in growth rates of a whole bunch of species that live in the coasts and the oceans, changes in recruitment, and indeed we've actually seen some of that already. Changes in abundance and catchability of species that prefer warmer or cooler waters, and potential declines in species that are really important for habitat forming. So things like kelps, which you can see on the right hand side there, are particularly affected by warming. So ocean currents and circulation are also another big one. So changes in sea surface height are associated with ocean warming and with meltwater input. And they in turn influence global scale circulation patterns, and they influence the occurrence of and the intensity of storms and waves, and they have a big influence on stratification of water masses, which affects productivity. So in the South Pacific around New Zealand, there have already been changes noted over the last 20 to 30 years. And the East Australian current, which is shown, the East Australian current, which is shown on that map, and the Antarctic circumpolar current have both already shifted southward. In terms of what's projected to happen in the future, I think it's pretty safe to say that predicting how global and regional circulation is going to change in the future is pretty tricky. But changes in these circulation patterns are pretty important because they can affect what species end up where, and whether or not they might establish there. But the specifics of that are also not particularly well understood yet. Ocean primary productivity as measured by chlorophyll is also really important. So there have been decreases in that in some areas around the country and increases in other areas. But that productivity is super important because it sinks into deeper waters below where that flux fuels ocean productivity. So actually around New Zealand, the projections for the end of the century are that it's not going to change so much around here than it compared to globally, but there are decreases in detrital flux that are predicted, and they're actually quite large, like 11 to 23%. So obviously changes in productivity and detrital flux have big implications for food supply, and particularly from surface to the deeper waters, which support a lot of deep sea fisheries and important communities. With lots of increases in winds and waves and stuff, which we've actually seen a lot of evidence of, sadly, in Canterbury in the last couple of weeks, you can expect that there will be heaps more input of fresh water into coastal zones, and a lot more sediment inputs as well through coastal erosion. You can expect that there will be more coastal erosion on the east coast of both islands because of its geography and geology and the coastal conditions there. And in turn, that can potentially cause quite a lot of degradation in habitats, and we've already seen that in coastal areas so far. So we get smothering of the seafloor in some instances, much more occurrence of very fine sediments, and which are easily resuspended and are not so good if you're a filter feeding organism, or if you're a tiny larva trying to find a spot to establish and grow. A lot of catchment runoff also affects water quality, so you get increases in bacterial load, increased nutrients, and also big effects on light levels, which have effects on kelps and other macroalgae species. Also, if you have a lot more of these sediments in the water column and in the areas, then they can be more easily resuspended by storms and waves. Ocean acidification is another one that we shouldn't forget about. So it's not strictly climate change, but it's super, super important. And it's happening around New Zealand at the same rate as it is globally. So this map shows the red line is basically that the increase over the last 20 years in atmospheric CO2 concentrations, which have been measured at Bering Head, just across the harbour there. The dashed white line shows the equivalent CO2 concentrations in the seawater, which are measured off in a long-term time series off the Otago coast called the Munida time series. And the white line shows the corresponding decrease in pH. So pH has declined in the open ocean from around about 8.09 to 8.065, which doesn't sound like a lot, but this is on a log scale. And so you're talking about a 7% increase in acidity of the seawater over that 20-year time period. So at the end of the century, they're projecting that in the open ocean, there'll be a decline of 0.33 pH units, which is quite a lot. And also the shallowing of the aragonite saturation horizon, which I won't go into the details of now, but basically some of it's a form of carbonate where it basically starts to dissolve below a certain depth in the ocean. So in terms of what that's going to mean for the marine environment, it's not clear how a lot of fish species and stocks around New Zealand are going to cope with that, because we really don't know how they're likely to be affected by ocean acidification. But we do know that in a lot of species, you end up with reduced larval survival, growth, biomass, that kind of thing, and it can affect reproductive outputs. Deep sea cold water corals and other vulnerable species that live very deep are also likely to be affected. And a lot of these things, while they may not be directly affected themselves, can be because they feed on a lot of these other organisms that will be affected. So coastal acidification is a big deal. We don't actually have a lot of we don't have any long-term time series on how the pH of the ocean is changing in the coast. And about 5 years ago, Kim Curry from Otago University and NIWA set up a nationwide monitoring series, which basically has 14 sites now, which is pretty awesome. And in the short time that it's been going, it's shown that there's really large variability in pH in the coastal area, way more than you see in the open ocean. It varies between sites depending on how much oceanic influence there is, how much riverine input there is, and what's coming off the catchment as well. Interestingly, photosynthesis in kelp beds helps to mitigate changes in acidification, which is a pretty interesting thing to think of as a management tool going forward, perhaps. And the implications of all that include that that some areas will be more affected than others, and it's not a simple picture like it is out in the ocean. So we've done a lot of work as part of a project called CARIM, which has just finished. It was a 5-year MB funded project looking at different species, and I'll just give you 2 examples. So we looked at the life cycle of the paua and how that was affected by ocean acidification. We found that the early life history stages of the paua were very severely affected in laboratory experiments. They don't cope particularly well at all. We found that juveniles can show some negative effects, but it depends on where the juveniles are and what they've experienced in their lifetime previous. And adults weren't noticeably affected, but sadly, under conditions predicted for the end of the century, they didn't spawn particularly well. So there are things to think about in terms of maybe coming up with some strategies to ensure that there's successful spawning and early development at those critical life stages. And also a healthy environment is going to be absolutely critical. So the paua out in the wild need to be in an area that's not negatively influenced by coastal inputs and stuff like that. Norman Ragg and his colleagues from Cawthron did a similar kind of study with green-lipped mussels. And in contrast to the paua, actually, most of the life stages were remarkably resilient to ocean acidification. Norman did notice that the very young larvae are going to be a survival bottleneck. So that's just for probably like a 48-hour period. And he also noticed that what the parents had experienced, so how resilient they were to acidification, flowed onto their offspring. So that's something also to think about in terms of managing those species and areas, but have to be super careful about when those crucial life stages are going to be exposed to low pH. So my final slide, just to sum up, that we really need to consider the multiple environmental factors that are likely to change. I've talked about only a few of them, remembering that they're not going to work just, one at a time. They'll all be kind of interacting in weird ways that we really don't understand. But we need to keep that in mind when planning marine protected areas. Doing risk and sensitivity assessments, are extremely useful. And we've done some of that in a recent project, which I can talk about later on if anyone is interested. And they can be really useful in helping to mitigate strategies or and things that may or may not work in terms of trying to keep these communities and areas happy and healthy. There is a lot that we don't know. We don't know a lot about particularly fisheries species and all different stages of their life cycles. So getting together and evaluating what's important from all sorts of different perspectives and coming up with a consensus is the way to go. Okay, thank you.